Hello! In this video, we're going to prove the following theorem. The set of natural numbers, along with the function sigma, which maps each natural number to its successor, and the empty set, which acts as the zero element, is a Peano system. Now, our definition of a Peano system is as follows. Suppose P is a set, S is a function from P to P, and E is an element of P. Then the triple P, S, E is said to be a Peano system if S is an injective function, E is not an output value of the function S, and for every subset A of P that contains E and is closed under S, we have that A is equal to P. Now, to say that A is closed under S means for all elements N in A, S of N is an element of A as well. So before we get into proving this theorem, let's first get a little bit more context. First of all, if A is a set, then the successor of A is given by the union of A and the singleton set of A. And next, a set I is said to be an inductive set if the empty set is an element of I, and for every element n in I, the successor of n belongs to I as well. Now, a natural number is a set which belongs to every inductive set. And at this point, we have proven that there exists a set whose members are exactly the natural numbers. And we denote that set by the Greek letter omega. Now, we've also proven that the set of natural numbers, omega, is an inductive set, meaning the empty set is an element of omega, and for every element n in omega, the successor of n also belongs to omega. We also have the principle of induction, which we have proven, and it says the following. It says if S is a subset of the natural numbers and S is an inductive set, then S is equal to the set of natural numbers. And another fact about natural numbers that we're going to be using is that every natural number is a transitive set. Or in other words, if n is any natural number, then for any sets x and y such that x is an element of y and y is an element of n, we have that x is an element of n. Now, we're also going to be using some properties involving the union of a set. And the way that the union of a set works is as follows. Given that x and a are sets, well then, to say that x is an element of the union of A means that x is an element of some set in A. Or in other words, there exists a set y in A such that x is an element of y. Now, some properties involving the union of a set that we're going to be using in proving this theorem are as follows. Given A and B are any two sets, well then the union of the union of A and the union of B is equal to the union of A and B. And if A is any set, then the union of the singleton set of A is equal to A. Now, we've done a video in the past where we proved this first property. As for the second property, well, we can prove this right away as follows. First of all, if we consider an arbitrary element x in the union of the singleton set of A, well then, by definition, this means that x is an element of some set in the singleton set of A. So, there exists a set y in the singleton set of A such that x is an element of y. So since y is an element of the singleton set of A, well, that means y has to be equal to A. So since y is equal to A and x is an element of y, well, we can take y in this statement and substitute for A, and so we have x is an element of A. So this shows if X is any element of the union of the singleton set of A, then X must be an element of A. And therefore, the union of the singleton set of A is a subset of A. But now to show the other inclusion holds, that is, to show A is a subset of the union of the singleton set of A, well, if we consider an arbitrary element X in A, well then we immediately see there exists an element Y in the singleton set of A, such that X is an element of Y. Right? Just take Y to be A. Well, in that case, we know A is an element of the singleton set of A, and we know X is an element of A. That's what we have here. So this statement is indeed true. And that's precisely what it means by definition for X to be an element of the union of the singleton set of A. It means that X is an element of some set in the singleton set of A. And so this shows that the other inclusion is true, right? And therefore the two sets are equal. Okay, so this is what we're going to be using in proving this theorem. So now let's get into proving this theorem. And actually, what we should mention first is, we should first note that this triple satisfies these first three conditions. And to see how that happens, well, we know that omega is a set. We know that sigma is a function from omega to omega. The reason why is because we know for any natural number n, the successor of n is also a natural number. Right? That's precisely what we have here. And finally, we know that the empty set is an element of omega. That's what we have right here. So this triple satisfies the first three conditions in order to be a Peano system. So now, to verify that this triple is a Peano system, we want to verify these three conditions are true. So now, let's prove those three conditions hold. Now, to prove that this triple satisfies these three conditions, we're actually going to prove these three conditions in reverse order, just by preference. So we're first going to prove the third condition is true for this triple. And to prove this third condition, let's give ourselves an arbitrary subset A of the natural numbers that contains the empty set, and A is closed under sigma. Now, since A is closed under sigma, remember, this is another way of saying for all elements n in A, sigma of n belongs to A as well. Or in other words, by definition of sigma, sigma of n is the successor of n. So this is really saying for all elements n in A, the successor of n belongs to A. And so what do we see here? We see that the empty set belongs to A, and for all elements n in A, the successor of n belongs to A. These two facts tell us that A is an inductive set. So, since A is inductive and A is a subset of the natural numbers, well, from the principle of induction, that implies that A is equal to the set of natural numbers. And that is exactly what we set out to prove in order to prove that the third condition is true. So that proves that the third condition is true. Now we're going to prove that the second condition is true. To prove the second condition is true, we're trying to prove that the empty set is not an output value of the function sigma. So to prove that, well, let's assume for a contradiction, we instead have that the empty set is an output value of the function sigma. Well, in that case, that means that the empty set is the successor of some natural number. I'll call that natural number n. But then what happens? Well, m is an element of the singleton set of m. And the singleton set of m is a subset of the union of m and the singleton set of m, which is equal to the successor of m. And the successor of m is equal to the empty set. So this shows that m is an element of the empty set. But that contradicts the fact that the empty set has no elements. Our assumption that the empty set is an output value of the function sigma led us to a contradiction. So we must instead have that the empty set is not an output value of the function sigma. So that verifies the second condition is true. Now we're going to verify the first condition. We're trying to prove that sigma is an injective function. To prove that sigma is injective, we're trying to prove for every natural numbers a and b, if the successor of a is equal to the successor of b, then a is equal to b. So to prove that, let's give ourselves two arbitrary natural numbers, a and b, and we'll suppose that the successor of a is equal to the successor of b. And to prove injectivity, we want to show that a is equal to b. Now, the trick here is, since the successor of a is equal to the successor of b, it follows that the union of the successor of a is equal to the union of the successor of b. But then, we know that the successor of a is equal to the union of a in the singleton set of a. But then, from that first property of unions we were looking at, we're able to distribute the union across. So we have this. But then, we know that the union of the singleton set of a is equal to a. So we have this. And we can do a similar thing for b. So we know that the successor of b is equal to the union of b and the singleton set of b. But then, from that property of unions, we're able to distribute the union across. So we get this, but then the union of the singleton set of b is equal to b. So we have this. So this shows that the union of a and a is equal to the union of b and b. So then, remember, the whole goal is to show a is equal to b. And to show that, we're going to show that a is a subset of b and b is a subset of a. To show that a is a subset of b, let's give ourselves an arbitrary element x in a. Well, since x is an element of a, it follows that x is an element of the union of a and a, and therefore x is an element of the union of b and b. And so, either x is an element of the union of b, or x is an element of b. If x is an element of b, then we're done. So from now on, let's assume x is an element of the union of b. If x is an element of the union of b, this means that x is an element of some set in b. So in other words, there exists a set y in b such that x is an element of y. So what we see here is x is an element of y and y is an element of b. But remember, b is a natural number, and every natural number is a transitive set. So b is a transitive set. Because b is a transitive set, well, since x is an element of y and y is an element of b, that implies x is an element of b. So now let's put this all together. We have shown if x is any element of a, then it follows that x is an element of b. So that proves a is a subset of b. To prove that b is a subset of a, we're going to end up doing a really similar thing. So to do that, we would suppose x is an arbitrary element of b. Well then, since x is an element of b, that implies x is an element of the union of b and b, and therefore x is an element of the union of a and a. So either x is an element of a, or x is an element of the union of a. If x is an element of a, then we're done. So from now on, we'll assume x is an element of the union of a. Well, in that case, this means x is an element of some set in a. And I'll call that set y. So there exists a set y in a such that x is an element of y. Well, what do we see here? Since a is a natural number, a is a transitive set. So since a is a transitive set, well, from the fact that x is an element of y and y is an element of a, it follows that x is an element of a. And so this shows if x is any element of b, then x is an element of a, and therefore b is a subset of a. So we see that A is a subset of B and B is a subset of A, therefore A is equal to B. So now putting this all together now, we have shown if A and B are any two natural numbers, if the successor of A is equal to the successor of B, then A is equal to B. So that shows that sigma is an injective function. And so that verifies that condition 1 is true for a Peano system. So at this point we have shown, oh I forgot, I didn't mean to write 3, I meant to write 1. This shows that all 3 conditions are true for a Peano system for this triple. So this completes the proof. And so yeah, that's pretty much it for this video.